The quantum lens on time. In laboratories across the world, physicists are approaching the concept of time travel not with DeLoreans or phone booths, but with carefully controlled quantum systems and mathematical models. Dr. Seth Lloyd of MIT stands among the pioneers in this field. In 2011, he demonstrated that quantum mechanics might allow for closed time-like curves, CTCs, theoretical paths through spacetime that return to their starting point in both place and time, to be simulated in quantum systems. This doesn't mean sending physical objects backward in time, but rather creating quantum states that process information as if they could interact with their own past. The research began as a theoretical pursuit. Physicist David Deutsch had proposed in 1991 that quantum mechanics might resolve the paradoxes that plague time travel theories in classical physics. Lloyd took this further by showing how quantum computers could be programmed to simulate these paradox-resolving behaviors. At the Australian National University in 2014, researchers led by Dr. Martin Ringbauer implemented a simplified version of Lloyd's proposal. Using polarized photons, they simulated quantum particles traveling through CTCs. The experiment demonstrated that information could behave in ways consistent with interacting with its own past, without actually violating causality in the physical world. What makes this research compelling isn't the prospect of building actual time machines, but rather what it reveals about the nature of quantum information and computation. These simulations suggest certain computational problems might be solved more efficiently using quantum systems arranged to mimic time travel mathematics. The work connects to fundamental questions in physics. If information can appear to travel backward in time within these simulations, what does this tell us about the arrow of time itself? How deeply is temporal directionality woven into the fabric of reality? As quantum computing technology advances, researchers continue refining these simulations, probing the boundaries between the possible and impossible. The quest isn't to build a time machine, but to understand time itself, perhaps the most elusive dimension of our existence, through the strange lens of quantum mechanics. In this field, today's experiments may help us understand tomorrow, not by traveling there, but by illuminating the very nature of time's passage through the remarkable properties of quantum systems.